Hello everyone, welcome to lecture 24. Today we're going to start talking about oscillatory motion or harmonic motion, and we're going to introduce a very important concept known as the simple harmonic oscillator. So just as a quick note before we get started, we just finished chapter 10, which was rotational motion, and then for the purposes of this class we're going to go ahead and skip through 11 through 13. Very important, exciting material, but we will not cover it. And the rest of the class is going to be talking about basically harmonic motion and the related phenomenon of waves. So that's chapters 14 through 16. We won't actually do all of chapter 16, but that's going to be the rest of the, I guess, 2.5 weeks of class here. All right, so today we're picking up with chapter 14, which, as I mentioned, is harmonic motion. So the idea behind harmonic motion is there's this very general thing that you've seen in many circumstances, which is things in nature like to move back and forth periodically. So I have a bunch of examples of this that I grabbed from around my house. A good example you're familiar with is a pendulum. Here is the pendulum I was able to find. So this little Beethoven monkey toy, it plays Beethoven. If I press the button, oscillates back and forth. If I were to have no friction, it would keep going like a clock. Slinkies, very good example. Back and forth. This is a much slower period of oscillation. But again, in the absence of friction, slinkies or springs are a good example. And something I'm going to keep coming back to, if I have an object somewhere near the bottom of a potential. So here it's at the bottom of potential. Here I'm going to kind of tilt it a little and hopefully you guys can all see. So I have my potential energy surface here. And if I put it near the bottom and move it a little to the side, it's going to oscillate back and forth near the bottom of that potential energy surface. So these are all examples of what's called harmonic motion. And it turns out there are many more. Just a few examples here. So pendulous springs we talked about. We'll talk about sound waves. Those are waves of the pressure in the atmosphere. Water waves, we'll also talk about that when we cover waves. And then for those of you who go on, light is an electromagnetic wave. That's something we'll cover in 23-26. Another good example of that is the alternating current that comes out of the wall. So hopefully you guys are watching this on something with power. You are using alternating current. You're using harmonic motion in order to power your device. So it's a very common thing in nature. And the truth of the matter is it's actually at the heart of 99% of the problems that we can actually solve. So we refer to oscillating motion, something that goes back and forth like that, as harmonic motion or oscillation. And it's, as I mentioned, it's the building block of electromagnetic waves. It's actually going to be, these AC circuits are the starting point of most electrical engineering projects. So those of you who want to go on to electrical engineering, you don't have a choice. You're going to be doing a lot of alternating current circuits or harmonic oscillators. Another big thing close to my heart, quantum mechanics. So actually the starting point of quantum mechanics is to break systems down into these little modes, these little pieces that oscillate back and forth, called modes or eigenstates. And then what you do is you just fill them up with particles and see how they go. That's the quantum of quantum mechanics, is breaking it up into these little fundamental pieces of oscillatory motion, which are called quanta, and then filling them up. And many more things. In fact, I'll be perfectly honest. So I am a theoretical physicist. I do that for a living. And I would say 40% of our active research, maybe more of that if you really want to just consider pencil and paper research and not computational, is taking a complicated problem and reducing it to the closest harmonic oscillator approximation. So very large percentage of physics is based around the idea of harmonic motion and the related concept, which we'll talk about in the next chapter, of waves. So in this chapter, we're going to start to learn the math and the physics behind why this is everywhere. We'll learn how to describe, how to understand that oscillation, and we're going to do a heck of a lot of calculus to get very comfortable going back and forth between various descriptions of those oscillations. All right, so first off, when do we expect harmonic motion? The idea is basically that it's very common because harmonic motion will happen near any stable equilibrium. So if we go back to those examples I was showing you, we had our pendulum. What's the stable equilibrium of the pendulum? Just point straight down. If I move it a little away, it tends to try to come back towards that stable equilibrium. In the absence of damping, it would just go there forever. If I have this slinky, here's stable equilibrium, and if I move it a little away, it tends to oscillate around that stable equilibrium. And this example that I love to come back to, a ball in a potential, here is the stable equilibrium. If I move it a little away, it will move around that stable equilibrium. All right, so this is going to turn out to be everything in harmonic motion. Here I've drawn one of these lovely potential energy graphs that everyone knows and loves. So here, for example, is for a spring. Potential energy is 1/2 kx squared. So as a quick reminder, what I'm plotting here is the potential energy curve, that's what's drawn in blue, as a function of the position x. So the stable equilibrium, remember, is the bottom of that potential, kind of like when the ball was at the bottom of the bucket, as I was just showing. And if I put it right there with no initial potential kinetic energy, it just stays there forever. That's why we call it a stable equilibrium. If I move it a little bit away, for example, if I move it to the left, the force tries to bring it downhill. The force accelerates it towards the stable equilibrium. And similarly, if I bring it up on the right side of the hill, the force accelerates it towards the stable equilibrium. So as soon as I move it away from the stable equilibrium, it wants to restore itself to stable equilibrium, which we call a restoring force. And as you see, that restoring force is going to try to bring it back and forth through the stable equilibrium, essentially infinitely often, if we have conservation of energy. It'll just keep oscillating back and forth between these maximal potential energy points. So it always falls downhill. Another good example of this is a spring on a glider on an air track connected to a spring. So this is something we'll keep coming back to throughout this class. It's one of the few examples where we have a very nice analytical solution. So here we go. I have a mass oscillating on an air track. So this guy's going to turn on an air track, is actually connected to 2 springs, not 1.
Approximately constant amplitude. Let me see if I can.
You'll notice it just keeps going
my hand in
back
some
and
fixed
forth.
place.
Essentially infinitely long if I were able to forget about friction. So again, notice if I displace the force, the mass a little to the right, the force pulls it back to equilibrium, pulls it to the left. If I displace the mass a little bit to the left, the force pulls it to the right. Again, it restores it to equilibrium. So this is the general property of harmonic motion. It happens near stable equilibrium, any stable equilibrium. And the idea is that when we displace the cart from its equilibrium, the spring or whatever other force is causing this potential energy creates a restoring force, which pushes it back towards equilibrium. Restoring force because it restores equilibrium. And then the general property, as I mentioned, it's going to go back and forth around that equilibrium position, which we refer to as harmonic or periodic motion. All right, so let's start. Before we describe all the math, we just need to kind of characterize what is periodic motion. So there are 2 big things you can see in this plot. If I plot out the position as a function of time, it looks something like this. It starts out at some maximum value, let's say. It goes down, goes to some minimum value, and comes back. There are 2 obvious things that I can use to characterize this. One is how big the oscillations are. How far does it go from its maximum value to its minimum value? And that is referred to as the amplitude A. Specifically, the amplitude is defined as the maximum displacement from equilibrium. So if the equilibrium here is denoted by O, and the maximum displacement is up here, then that distance, that spatial distance, is A. And similarly, it will go A below equilibrium as well. So that's my amplitude, maximum displacement from equilibrium. A formula, if you guys like formulas for calculating this, one way to do it is the maximum value of x minus the minimum value of x over 2. So in this case, that would be A minus negative A divided by 2 is going to give me that amplitude A. The second quantity that's going to characterize periodic motion is the period, t, which is kind of the time that it takes to repeat itself. So if I start out with my object displaced as far as possible in the positive direction, let's say I move it a meter to the right, let go, and then eventually it comes back to that same point, and then I do the same cycle and it comes back to the same point, and so on, the amount of time that it takes before it repeats itself, capital T, is called the period to complete one cycle. So the amplitude and the period are the two major ways of characterizing simple harmonic motion. Now the period is not all that useful mathematically. It's kind of a pain in the butt to work with. Kind of similar to what we saw in rotational motion, we're going to describe it a couple of equivalent ways. So one that you're probably familiar with is the frequency. The frequency tells me how many times does the object go through a cycle per every second. So let's say that it went through 1, 2, 3 cycles in 1 second. Then I would say that the frequency in that case is 3 cycles per 1 second, or 3. And the units of 1/seconds are called hertz. So the frequency tells me how many cycles I go in a certain amount of time. Now you can think about this for a second, and what you'll quickly realize is that the frequency is simply the inverse of the period. Frequency f is 1/t. And so that's going to be somewhat useful. For example, when I'm talking about a laser or sound waves, frequency is a very common way of referring to how fast the oscillations are. That said, we're going to be doing a lot of math in this class, and what we like in math are radians. So what is the natural unit, what is the natural way of talking about angular motion? Well, it's angular frequency. And so angular frequency, very similar to angular velocity, is denoted by omega. And again, if you work through the same bit of physics, it's 2 pi radians in a period t. So the angular frequency is 2 pi divided by t, or in other words, 2 pi times f. So these are 3 equivalent ways to describe the period. And what you're going to want to do is you're going to get very comfortable going back and forth between them. I'll usually give you one of them, and then you have to go to another one. As a rule of thumb, if in doubt, always convert to angular frequency. That's your best bet. That's far and away the easiest mathematically. But sometimes the problem will ask for one of the other ones, and then you're going to need to be able to go back and forth between them. All right, so these are the 2 biggies. Amplitude A and period T, or equivalently frequency, or equivalently angular frequency omega. There's one other thing that we need to be a little bit more clear about what's going on, which is to tell people where exactly we are in the cycle. So here, for example, let's say that I just define t equals 0 here as the start of the cycle, the maximum of that cosine, for example. Then I need to be able to clarify to someone, well, when do I tell them that I'm here, or here, or here, or here? And in the same way that I would clarify for rotating objects where I am by an angle, theta, I will tell people where I am in the oscillations by an angle called the phase, capital Phi. And this you should think of as just an angle in radians, which tells me where I am in the cycle. Generally speaking, there's really no way, you just have to tell people what you're calling phase 0. So for example, let's say I define the starting point here as phase 0, then it's pretty clear what I should label the rest of the points. So for example, what's the phase that I should pick for when it comes back to itself for the first time? So that's not phase 0, let me be clear. You don't want to call that phase 0 because phase 0 refers to the starting point. Here it's repeated itself, but it's gone through a whole cycle. So what do I call one revolution or one cycle? How many radians? So that's just going to be 2 pi radians. And similarly, if I'm halfway along the cycle, how many radians is that? That's just pi radians. So 0, pi, 2 pi radians, and so on. You can see clearly that as I progress in time, I'm progressing in phase. My angular phase, for this particular case, if t equals 0 corresponds to phi equals 0, I'm going to tell you that the phase is just omega times t. And if we want to check that, let's check what happens at t equals capital T. So that's omega times capital T. Omega, remember, is 2 pi divided by t. So that tells us that time t, I have phase of 2 pi, which works out. All right? So that just tells me where I am in the cycle. It's a little bit less fundamental, but it is kind of useful. All right, so let's get a little bit of practice on this. I've drawn out a graph here of some buoy that's moving up and down in the water in periodic motion. And based on my drawing here, so it's not going to be perfect, but I want you to do your best to use this graph. Try to figure out what's the approximate amplitude, period, frequency, and angular frequency. Okay, very good. So hopefully you've had a chance to pause the video, try out this problem. We're going to do it in our PDF in a quick second, but before that, let's just go ahead and draw out some key points here. So I have this harmonic motion. The useful things, as you may remember, are where does it hit its maximal value, where does it hit its minimal value, and what are the times corresponding to those. So let's go ahead and figure those out. First off, this maximal value here is somewhere between y equals 1 centimeter and y equals 2 centimeters. Let's call that maybe y equals 1.4 centimeters. And similarly, if I draw the minimal value here, that's roughly at negative 1.4 centimeters. Okay, so y max, here y is the vertical position, is 1.4 centimeters, and similarly y min is negative 1.4 centimeters. So we can quickly figure out the amplitude. I don't even need to go into my next slide. I'm just going to tell you the amplitude is the distance between equilibrium, which is 0, and maximum, which is 1.4 centimeters. The amplitude is 1.4 centimeters, or if you like SI units, 0.014 meters. Okay, so that's the amplitude. Now let's talk about the frequency. So actually, if I give you a drawing like this, the easiest thing is going to be the period, because I'm already telling you about time. In order to do that, let's go ahead and see what's happening at the maxima and the minima. So here's the first maximum, here's the second minimum, first minimum, second maximum, second minimum, and so on. So let's just go ahead and draw these all out really quickly. And if I want to calculate a pretty accurate period, what I want to do is I want to use multiple cycles. So I could use one cycle. If I take the time difference here, that would be t. If I take the time difference here, that would be t again. It comes from a maximum to a maximum. Remember, maximum to maximum, that's your period. Maximum to minimum, that's half the period. So there are 3 periods, and the next one is off the figure, so we'll use these 3. Now time here, I have 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7, 8. And if I look at this first maximum, that's somewhere between 0 and 1 second, I'm going to call that maybe 0.3 seconds. And if I look at the third maximum right here, the fourth maximum right here, somewhere between 7 and 8, I'm going to call that maybe 7.2 seconds, something like that. Okay, so it goes from 0.3 seconds to 7.2 seconds. That means the amount of time elapsed between the starting and the ending, 0.3 and 7.2, is 7.2 seconds minus 0.3 seconds, or 6.9 seconds. And now, if I want to figure out the period, what I'll notice is that that's just 3 times the period. Notice that there are 1, 2, 3 times the period within that period of time. So t is 6.9 seconds over 3, which is just 2.3 seconds. And now quickly I can go ahead and convert that into frequency or angular frequency. So for example, my frequency f is 1 over t. Sorry about that. Go ahead and erase that. So 1 over t. You plug in 1 over 2.3 seconds, you get 0.43. The units are inverse seconds or cycles per second, but as a quick reminder, we can also call that hertz, Hz. And the angular frequency is just 2 pi divided by t, or 2 pi times f. Either way, when you plug that in, you get 2.7. And just like rotational motion, the units of omega are radians per second, or equivalently just inverse seconds. You could also write hertz. That's the same thing. It's just for various reasons it's very uncommon to do that. But anyways, 2.7 is your omega. Alrighty, so that's harmonic motion. Now the rest of today's class is going to be talking about a very special, very, very important example of harmonic motion called simple harmonic motion. That word simple makes all the difference. And this is the special case where the restoring force is proportional to displacement. So the restoring force is some constant times the displacement. And that looks pretty familiar, right? F equals negative k times x. That is just a spring. So this is basically the physics of oscillations of a spring. For example, my slinky, or if we go back to our pretty video, when I have two springs attached to a mass, that's going to be, in the absence of friction, simple harmonic motion. All right, so let's work through the math on what happens when I have a spring, when I have force proportional to k times x happening on my object. So first off, the equations of motion are very simple. If the only force is negative k times x, then my force is equal to mass times acceleration, which is equal to negative k times x. And as a quick reminder, acceleration can also be written as the second derivative of x. So mass times the second derivative of x is equal to negative k times x. Those are my equations of motion for the spring. Before, we weren't actually solving this. We were just doing energy. Now we're going to solve it. Okay? So we're going to solve that on the next slide. Before we do that, I just want to quickly mention a couple of important things. Notice that my acceleration and my x, displacement, have opposite signs in this equation. So when the acceleration is positive, x is negative, and when the acceleration is negative, x is positive. So that's a consequence of the fact that I have a negative sign for the restoring force, which tells me the acceleration is always going to try to bring x back towards zero. That'll also be relevant down the road when we're solving for acceleration in these problems. The other very, very important thing, hopefully it's obvious, but I do feel like I should say this, acceleration is absolutely not constant in simple harmonic motion. It's k times x, and x is changing as a function of time. So absolutely do not use the equations for constant acceleration in any part of this chapter. If you do so, you will immediately get it wrong, I promise you. Okay? We do not have that choice. Instead, we are going to have to solve this full equation of motion, mass times acceleration is equal to negative k times x. And that's now what we're going to do. We're going to actually do a little bit of calculus. So when we have an equation relating derivatives of x to x itself, or various derivatives of x to other derivatives of x, that's what's called a differential equation. For those of you who go on to do more mathematical things, whether it's physics, chemistry, or just math, you're going to have to solve a ton of these down the road. This is a particularly easy one called an ordinary differential equation, but it gets worse. That said, we're only going to solve this one right here. And we're going to do that by starting with a slightly easier one. So what I want you to do, I actually want you to take a couple of minutes here and see if you can guess the following thing. Let's say I were to forget about m and k and just tell you that d squared x dt squared is negative x. So the second derivative is proportional to negative the function. So can you figure out a function that satisfies this equation? A simple function that you're all know and love that satisfies this equation. I'm going to give you a quick little hint, which is we know that the solution to this kind of looks like periodic motion. All right, so what function satisfies this equation? All right, hopefully you've had a chance to think about this. I really want you to try to write down a solution to this equation before we go on. Hopefully you've done so. So there are actually a couple of answers. Usually if we were doing this in class, I'd probe the class. I'd say, tell me an answer. So one of them that I usually get is x is equal to sine of t, right? So we take one derivative, we get time derivative. We can write that as x dot is cosine. We take one more derivative, x double dot, the acceleration is negative sine, which is negative x. That works. Another answer people give me is cosine. You take one derivative, you get negative sine. You take another derivative, you get negative cosine. So that also works. And it turns out there's a whole class of solutions. If I add up any of these two solutions, I get an answer that works. So it will turn out that the general answer to this differential equation is b cosine t plus c sine t. Or with a little bit of trig identities, I can also write that as a cosine t minus t0. All right. So now that we've warmed up with this simpler example, let's talk about the more general differential equation. md squared x is equal to negative k times x. All right, so for those of you who are going on, how do I solve this type of differential equation? You'd think it would be very, very clever. It's absolutely not. You don't do anything clever. What you do is you guess an answer and you check that it works. So we're going to guess an answer. X is equal to a cosine omega t plus phi, and check to see that this works. All right? Sounds silly, but that is in fact how this is usually done in the first place. So this is simple harmonic motion, or a simple harmonic oscillator. And what we saw is that the equation we want to solve is md squared x dt squared is equal to negative k times x. All right, so let's guess a solution. X is equal to a cosine omega t plus lowercase phi. Here lowercase phi is like the initial phase, the phase at time equals 0. And what we're going to do is we're just going to take some derivatives. So let's take the first derivative of x with respect to time. So the way this works, I have a times the derivative of x with respect to this whole thing, which I'll call u. So u is going to be defined as omega t plus lowercase phi, or actually, in order to avoid some notation, let's just call that capital phi. That's our overall phase of the motion, which I introduced earlier. So we'll do the chain rule. This is dx, d capital phi times d capital phi dt. What's the derivative? I'm sorry, derivative of cosine, not x. So it's derivative of, let me rewrite this. Derivative of cosine phi d phi times the derivative of phi with respect to time. All right, so we'll do this piece by piece. What's the derivative of cosine? It's negative sine. So that's a times negative sine of that phase angle, which now I'll go ahead and write out as omega t plus lowercase phi. And what's the derivative of phi with respect to t? Well, the derivative of this lowercase phi is 0, because that's a constant. Derivative of omega t is just omega. And if I rewrite this around, my velocity in the x direction, dx dt, is just negative a omega sine omega t plus phi. And I've said that we're not going to do a ton of calculus in this class. This is one of the pieces of calculus that you really do need to be able to do. You need to be able to take derivatives of a given x to get velocity, and vice versa. You need to be able to take integrals to go back to x. So here we go. For this choice of x, that's the choice of velocity. Take one derivative. Let's take one more derivative. The acceleration in the x direction is the second derivative of x, or the first derivative of velocity. So again, that's pretty straightforward. That's negative a times omega, those are constants, they factorize, times the derivative of sine capital phi d phi. That's this guy, take a derivative, times d phi dt. The derivative of sine is cosine. The derivative of phi, again, is omega, so that's negative a omega cosine phi, which is omega t plus little phi, times omega. Or in other words, the acceleration is negative a omega squared times cosine of omega t plus phi. All right, so that's just from taking derivatives. Now I have the acceleration. I have my guess for x itself. And now let's just go ahead and plug these into my Newton's equation. Mass times acceleration is equal to negative k times x. So I have mass times acceleration, that's negative a omega squared cosine omega t plus phi is equal to negative k times x, which is just negative k times x, which is a cosine omega t plus phi. So what do I have to do to get these two sides of the equation to match up? Notice that they both have negative signs, they both have a's, and they both have cosine omega t plus phi. So the only thing I have to do is to get the rest to match up. And I'm sorry, this is mass times acceleration. There should be an m here. Let me quickly rewrite that here. So when I do mass times acceleration, I have negative a omega squared times m times cosine of omega t plus lowercase phi. So again, everything matches up if omega squared times m is equal to k. And in the end, we want to solve for omega. That's the variable we don't know. So we'll divide both sides of the equation by m. We'll take a square root, and what we find is the angular frequency omega is the square root of k over m. If I write that, then x is equal to a cosine omega t plus phi is a solution to the differential equation. So that is the solution that we have here. Omega absolutely has to be equal to the square root of k over m, which is set by the mass of the object and the spring constant of the spring. It's a fundamental physical constant. That said, a and phi, they were completely arbitrary. Any values that I put in there will work. So those are what are called initial conditions. The size of the oscillation, the amplitude, and the phase of the oscillation, those are just set by how I choose to move my object. Omega is fundamental. That's set by the spring itself and the mass of the object. All right, so if we go back to our original way of describing motion, we can now identify what are these objects in our expression. The amplitude is A, omega is the angular frequency, and this whole thing sitting inside the cosine, that's the phase of the drive, right? So for example, when phase is 0, I'm at the maximum of that cosine. And we're going to now do a lot of work with this expression for our simple harmonic motion in order to understand it, and understand it particularly in the case of springs. So as a quick note, this lowercase phi, that's the initial phase, because if I set t equals to 0, my initial point in time, then my phase is just this lowercase phi. So that's my initial phase of the oscillations. All right. So quickly, before we go on to solve anything, I just really want to emphasize, when I change the amplitude or the phase, these initial conditions, the frequency does not change. I can make the oscillations very large or very small, and in the limit where this is simple harmonic motion, nothing should change about the amplitude. So here, if I have my spring, if I do very large oscillations or very small oscillations, those should, in principle, be exactly the same angular frequency, simply set by the mass of the spring, which is actually a little bit of a lie here, but that's fine, and the spring constant of my spring. So that's a very important thing that you're going to need to keep in mind. All right, so let's do an example of this. Imagine we go to that YouTube video. I pull a glider of mass 0.5 kilograms with a 6 Newton force, and that displaces it to a new equilibrium that's 0.03 meters away from where it started. And I let go. So what I want you to do is spend a couple of seconds here and solve what are the resulting frequency, angular frequency, and period of that glider. All right, so I'm going to assume you've had time to pause the video, try to solve this problem. Let's go over the answer together. So here, this is a glider, a mass on a spring. It is quintessential simple harmonic motion. And part A of the problem asks us for the frequency, angular frequency, or period. In this case, we're going to want to solve, as I mentioned, for angular frequency. That's always the pretty one. So the angular frequency, as I mentioned, is always going to be the square root of the spring constant K divided by the mass M. So we are given the mass M. We are given that it is 0.5 kilograms. 0.5 kilograms. We are not given the spring constant K, but what we're told is the following. I pull on the object with a force which is equal to 6 newtons, and it's in equilibrium, meaning that there is a spring force, K times the amount that I displaced, pulling it to the left, which in equilibrium we know is going to be 6 newtons as well. So 6 newtons is equal to K times the amount that I displaced it, which is told to us as 0.03 meters. And then just a quick line of algebra here. We can figure out that our spring constant K is simply going to be 200 newtons per meter. Alrighty, so K is 200 newtons per meter. I can now plug that into my original formula, and I find that omega is 20 inverse seconds, or 20 radians per second. And from there, everything else is easy. So for example, the frequency, so if omega is 2 pi times f, then frequency is omega over 2 pi, which is 3.2. Units are hertz. And the period t is 1 over f, which is 0.31 seconds. So once you have omega, everything else just falls into place. Quick, 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 quick. So there's not too much else to calculate here. That's very nice. But what I want you to do, I want you to think a little bit about what happens when I change things. All right? So there you go. I have this set up, the exact same spring constant and everything, but now, instead of releasing it from 0.03 meters, I'm going to release it from an initial displacement of 0.02 meters. So what I want you to tell me is what changes: angular frequency, period, amplitude, or multiple. So let's go through it one by one. Does angular frequency change, yes or no? The answer is no. Angular frequency is the square root of K divided by M, always. K is constant. It's 200 newtons per meter. M is constant at 0.5 kilograms, so angular frequency does not change. What about the period? No. Period does not change because period is just the same as angular frequency. They're one-to-one. They're exactly equivalent, just doing a little bit of algebra to go between one and the other. So period is 2 pi over omega. If omega is unchanged, period is unchanged. What about the amplitude? Does the amplitude change? So yes, the amplitude does change here because now I've got an initial position of 0.2 meters instead of 0.03 meters. So in my original one, my x as a function of time would be something like 0.03 times cosine of omega t, because I have my initial phase equal to 0. It's the maximal displacement. That's in meters. If I have my new one, my x is simply 0.02 meters times cosine of omega t. So the only thing that changes is the overall scale of those oscillations, how large they are, but the period or frequency do not change. It's a very important property of simple harmonic motion. That's actually what the simple in simple harmonic motion means. So we're going to keep coming back to this, but this is something I really want you to remember. All right, so we've talked about x, we've talked about omega, f, etc. You are going to need to be able to talk also about velocity and acceleration. So the equation of motion, that's what we call this, x equals a cosine omega t plus phi. That tells us everything about the simple harmonic motion. Once I solve for that, everything else kind of comes for free or with a little bit of calculus. So we've already done a little bit of calculus. I'm just going to repeat the results that I had earlier. For example, the velocity of the object, dx dt, we solve for that. That's negative omega sine, negative a omega sine omega t plus phi. And if you really like, you can rearrange this as a omega times cosine omega t plus phi plus pi over 2. You don't need to know that if you don't like, but it's just a little bit of trick. So if you plot that out, it looks as follows. It looks very similar to the x graph. It's also sinusoidal, but notice that when x is maximal, meaning the cosine is equal to 1, the velocity will be 0. When x is minimal, meaning that the cosine is negative 1, the sine is 0. And vice versa. When the velocity is very large, x is very small. So there's a nice complementarity between x and v, which we're going to use a lot. We can take one more derivative to get the acceleration. So that's negative a omega squared times cosine omega t. You could plot that out. The important thing to know about that, and really this is probably the most easy relationship you're going to use, is that simply negative omega squared times x. So if I rearranged my previous differential equation, what you would find is acceleration is negative omega squared times x, and that will always be the case, kind of by definition for simple harmonic motion. So yes, you could take a derivative to get acceleration, or you could simply use your knowledge of x and your knowledge of omega to directly get the acceleration without doing anything else. All right, so this is x velocity and acceleration. I don't think I have these formulas reproduced on the next slide, so you might want to keep this slide up on your home computer or whatever. And now let's go ahead and just solve another example of this. So now I have a 1.5 kilogram mass on a spring. The displacement is given by a cosine omega t plus phi with these given quantities. So what I want you to figure out is what's the time for one vibration, one maximum to the next maximum, what's the force constant of the spring, and what are the maximum speed and maximum force of the mass. In fact, I would invite you to go ahead and figure out what is the actual velocity and acceleration, or velocity and force as a function of time, and we can go from there. Alrighty, so let's go ahead and do this problem. Hopefully everyone's had a chance to do it on your own. So again, what are we given? We are given the following equation of motion. X is equal to a cosine omega t plus phi. One second. We're given that the amplitude is 7.4 centimeters or 0.074 meters. We're given that omega is 4.16 radians per second. And we're given this initial phase, which is an angle in radians, is negative 2.42, or if you like, negative 2.42 radians. As a reminder, this calculator's better be in radians from here on out in the course. And finally, the mass is 1.5 kilograms. So part A of the question asks, what's the time for one vibration? So we could solve that directly. My suggestion, as always, is let's start with omega. So actually, I don't even need to go anything crazy here. Let's just start with omega, which we know, and then we can easily convert this into a time. Right? So time is 2 pi divided by omega. I plug in my values of omega, and this is pretty straightforward. It is 1.51 seconds. That's how long it takes to go back and forth. Part B. What is the spring constant of the spring? So again, the heart of everything is omega. In this case, we're going to use the formula omega is root k over m for a mass oscillating on a spring. And we know everything except for k, so let's just go ahead and solve for it. So we square both sides. We multiply both sides by m. Then k is m, omega squared. Plug in some numbers, that's 26.0 newtons per meter. Part C. What is the maximum speed? The maximum magnitude of the velocity. So I always suggest here, just let's start by solving for the velocity itself. Velocity is dx dt, which we actually already solved on the slide. So that's just negative a omega times sine of omega t plus phi. And when is this largest? When is this equal to its maximum value? Well, its maximum is simply when the sine is equal to -1, right? So the sign goes between +1 and -1. If I want a maximum positive number, I need -1 times -1 gives me +1. And then Vx max is just a times omega, that coefficient out in front. So I know the amplitude, I know omega, I plug in these values, and it turns out that this is 0.308 meters per second. All right, so it's pretty straightforward. Once you're comfortable with these equations, you can kind of bing, bang, boom, go through them one by one. And this last little bit asks for the maximum force. So there are various ways I can do this. I'm actually going to do it two different ways just to show you it works. So option one is I could say that force is equal to -k times x. So it's just an object on a spring. There's nothing else happening to it. And so if I want to have the maximum force, I simply want the minimum value of x, right? Because there's a negative sign in front. So if I want the maximum positive force, I get the minimum -x. So that's just k times the maximum value of x. And remember, the maximum value of x is just the amplitude. So that's k times a. And when you plug this in, you will get 1.92 newtons. Another completely valid choice would be to say that the force is equal to the mass of that object times the acceleration. And the acceleration, remember I told you, is always negative omega squared times x. So again, the maximum force is going to be the mass times omega squared times x max, which is the amplitude. And lo and behold, when you plug in some numbers, this gives you the exact same result because m omega squared is equal to k. So that's the beauty of simple harmonic oscillators. These things all tie together very nicely due to the very simple motion that they undergo. All right, so you're going to want to get very comfortable with the equations. There's a ton of this on the homework. Don't worry, you'll get a chance. I want to quickly move on to one other thing before we, actually a couple other things before we end lecture today. So one is to say that the equation of motion contains all the information in the world. So we've seen one example of this. I can take derivatives. I can get velocity and acceleration from there. Another thing is that it tells us the relationship between some initial conditions. Let's say I told you the initial position and velocity, as well as the angular frequency, and you can figure out everything else from there. So this, it's just some algebra. I don't find it to be particularly interesting. Basically, the starting point is I have x of t is equal to a cosine omega t plus phi. And I tell you that at t equals 0, I have x0 is equal to a cosine of, well, if t is 0, that's just phi. And similarly for the velocity, I tell you that the total velocity is just negative a omega sine omega t plus phi. I plug in the value at t equals 0. I get v0 as negative a omega sine phi. And if I take these two equations, I can solve them for a and phi. It is not very interesting. It's just some algebra. But I invite you, if you're interested, you can take a look at that. It's in the posted notes. Anyways, the results after a little bit of math are that my initial phase is the arc tangent of v0x over negative omega x0. A little word of warning, this actually has two different solutions. So if you solve for the arc tangent, it has two solutions. Let's call it phi. And that same value plus pi radians. Okay, so there are two different solutions that you could get that both satisfy this equation. So you simply need to be careful to choose the correct one. And the way to do this is check that it gives correct value of x0 and v0. Okay, so plug them into the equations for x0 and v0 and check that it gives the right answer. The amplitude, there's no choice, is just the square root of x0 squared plus v0 squared over omega squared. So that's one thing that you can get out of x for free. I'm not going to go any more into details on that. You can just work on the algebra for the homework. The more important thing from my standpoint is that simple harmonic oscillators are an example of something that I keep emphasizing is really, really important in this class, which is conservation of energy. So as I keep mentioning when I talk about simple harmonic motion, this does not work in the case of friction. This is a case where energy is conserved, and therefore I can think of everything in the language of these energy diagrams. So you remember from these energy diagrams, what I'm thinking is there's a situation where energy is just going back and forth between kinetic energy and potential energy. All right, while the total energy is constant. So one way to do it is to look at this directly on the graph. If I have my potential energy here, let's say of a spring, so it should be a spring here because it's simple harmonic motion. My total energy is fixed. I can simply say that my kinetic energy is total energy minus U. And when I plot that up, I get this rightmost figure right here. Okay, so potential energy is an upward pointing parabola. Kinetic energy is a downward pointing parabola. And basically, as it goes back and forth between the maximum amplitude, where my kinetic energy is 0, and the negative amplitude, where my kinetic energy is also 0, you see that kinetic energy increases for a little bit, while potential energy goes down, and then vice versa. All right, so you can see that directly on this graph. I'm going to show this in a slightly better way by just looking at basically an object moving on a spring. So let's start off by talking at my initial maximum displacement. Let's say my x value is equal to negative a, my maximum displacement. What's the velocity of the object when it's at its maximum position? It's 0, right? So remember, always at the maximum position, it temporarily comes to a stop. My velocity is 0. And so at the maximum displacement, when I move my spring, let me just go ahead and show this as a video here. When I look at my simple harmonic motion, at my maximum displacement, my velocity is 0. And then it oscillates, okay? So let me show this oscillation. So stopped, 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 stopped. At the maxima and minima, it's temporarily stopping. In between, it's going through a position, the equilibrium position, where the velocity is maximal, or the kinetic energy is maximal. So if we think of that in terms of energy, at the maximum displacement, it's all potential energy. There's no kinetic energy. Temporarily comes to rest. As it goes towards equilibrium, it's going to speed up a little. It's going to pick up some velocity. So for example, if I'm at half my maximum position or half my maximum acceleration, my velocity will be non-zero. Here, I've taken some of that potential energy and I've moved it into kinetic energy. It's speeding up as it goes towards center. And notice as it oscillates back and forth, eventually it's going to come back and it's going to come through this exact same position moving to the left. So my speed, if you solve the math, is always square root of 3 over 4 V max. From energy conservation, it could be moving to the right or to the left, but in any case, my kinetic energy plus my potential energy is conserved. When it goes through equilibrium, 1/2 kx squared is 0. So my kinetic energy is at its maximal value. Kinetic energy is always maximum when it goes through that equilibrium position in simple harmonic oscillators. And then I continue on with my oscillation. So if I get halfway again, my kinetic energy is back to my velocity is back to root 3 over 4 V max. I get to my other maximum displacement when it's fully on the positive side. And again, it's all potential energy. So what you see is energy is conserved and it's sloshing back and forth between all potential energy when it's at the maximum displacements and all kinetic energy when it passes through equilibrium. So we're going to do one more quick example of this. I want you guys to give this a shot. Imagine a small block is attached to an ideal spring oscillating on a horizontal frictionless surface. The amplitude is 0.25 meters, period is 3.2 seconds. What I want you to figure out using energy is what are the speed and acceleration of the block when you are at x equals 0.16 meters. Okay, so let's go ahead and see what's going on here. You could solve this just using x as a function of t. I didn't tell you the initial phase. You'd have to kind of make a guess there, but you could solve that. You can try it on your own. It's not terrible, but it is actually kind of unpleasant. You have to do some inverse cosines. You have to do some kind of annoying stuff like that. And I generally recommend against that if you can avoid doing so. So situations where you don't actually need to know anything besides an overall velocity and overall x are actually very nice because I can use energy conservation methods. Okay, so consider my initial condition. My initial condition is when it's at its maximum displacement. So at maximum displacement, which is x max equal to the amplitude of the oscillation, which I believe I said was 0.25 meters. Let me double check that. Yes, 0.25 meters. What's the energy in the system? So at this maximum displacement, what's the kinetic energy in the system? It's 0, remember? So always at maximum and minimum displacements, when I'm as far away as possible, it temporarily comes to rest, the kinetic energy is 0. All of my energy is potential energy, which for a mass on a spring is 1/2 kx squared. And here my x is the amplitude a, so that's 1/2 ka squared. Notice that I don't know the spring constant, but that's okay. We're just going to leave it alone like this for now. All right, so my total energy in the system is kinetic plus potential. And in this case, that's just potential, so it's 1/2 ka squared. That is conserved. It's a constant. So now, if I consider this final point that the question is asking about, my x final is at 0.16 meters, some not particularly special value. And the question is, at this point, what do I know? So first off, do I know the speed or the kinetic energy? No, I absolutely don't. It's not told to me in the problem. I could solve for that, but I mean, it's actually asking me to solve for that in this problem, so we're going to go ahead and do that. My kinetic energy is also unknown. That's 1/2 mass of the object times v final squared, but I don't know what v is. And my potential energy, I kind of know. I know that it's 1/2 k times x final squared, but as before, I don't know what k is. So now, if I plug this into the equation, I have that my total energy is equal to 1/2 ka squared from earlier, and now it's equal to my final kinetic energy, because energy is conserved, so that's 1/2 m v final squared plus 1/2 k x final squared. All right, so nice thing, all those halves cancel, great. I know amplitude, and I know x final. But I'm not quite able to solve the problem yet because there are a few too many unknowns. However, I do know one other thing. I know that omega is the square root of k over m. And furthermore, I know that omega is 2 pi over t. I'm told that t is 3.2 seconds. So with a little bit of work, I can figure out that omega is, what do we have? 1.96 radians per second. Okay, so I do know omega. And notice that omega allows me to connect k and m, which are two unknowns in this problem. So let's go ahead and do that. I'm going to square both sides of this equation, multiply by m. I get that k is equal to m times omega squared. That's something we use a lot. And now I'll plug that into my energy conservation formula. So I have k, which is m omega squared times a squared, is equal to m times v final squared plus k again, which is m omega squared times x final squared. And now I'm cooking with gas because I can cancel out those masses. Everything's good, those are gone. And now I know every single thing in this formula except for v final. So we can go ahead and simply solve for that. V final, if I bring my x final over the other side, take a square root, I see that my final speed is the square root of omega squared factorizes times a squared minus x final squared. And you plug in some numbers. This is 0.377 meters per second. So when it moves through this point, when it comes through the first time, it's moving to the left at 3.77 meters per second. You know, if this is my initial displacement, and here's the point that I'm interested in, when it comes through the first time, it's moving to the left with 0.377 meters per second. Then it oscillates around, and the next time it comes back to the right at 0.377 meters per second. And so on. It keeps oscillating back and forth like this. All right, so that's my V final. That's the big energy conservation. There's one other thing it asks for, which is the acceleration. And there, I don't need to use energy conservation. That's a little bit easier. I'm going to simply use that my acceleration is simply negative omega squared times x. So that will always be the case. Here I want this at this final point, x final equals 0.16. And when I plug in the numbers that I know, that turns out to be negative 0.615 meters per second squared. Notice there's actually no question about the sign here. It's always negative because x is positive. So there will always be a relationship between those signs there. And there we go. All righty. So that is simple harmonic motion. The big things to remember from this lecture is the equation of motion for simple harmonic motion, the relationship between x, v, and acceleration, which we've solved. And the big one is energy is conserved in simple harmonic motion. You have rolling without slipping, or you have no friction, you have something like that. And therefore, we can solve everything very nicely using energy conservation methods. All right, so that's what I wanted to cover for today. I wanted to quickly mention where we're going next. So everything we've solved so far is basically a mass on a spring. But what I started out by telling you is that simple harmonic motion will happen near any stable minima. And you may have noticed that none of the examples I gave were just a mass oscillating on a horizontal spring. I had my, oscillating monkey toy or a ball on a ball in a bowl. So the key thing there is that it happens near any stable minimum, including that of a spring. And the kind of key point here is it really doesn't matter what's happening very far from that stable equilibrium. So here I plotted out the potential energy curve of a spring, 1/2 kx squared, and it's a beautiful parabola out to infinity. However, it wouldn't matter if at some point that spring goes off crazy and does some crazy potential energy curve like that. As long as where the particle is oscillating, it looks like 1/2 kx squared, it looks like a stable minimum, the physics is still just 1/2 kx squared. So that's the key to why simple harmonic motion is pretty much everywhere. It happens near any stable minimum. And what we're going to do next is we're going to put a little calculus to this claim. We're going to figure out the relationship between the oscillations and, it turns out, the second derivative of the potential energy. And then we're going to use that to motivate many different examples of simple harmonic motion. So pendula, physical pendula, other things like that. And even at the end of the day, we'll solve for a ball in a bowl, which is a completely general example of simple harmonic motion. All right, so with that, I will see everyone next time. Stay safe, stay healthy, and I will talk to you on next Tuesday.